Tile Roofing Industry Alliance presents changes to the 6th edition High Wind Tile Installation Manual issued in 2020. This new manual applies to all areas of Florida except for the high velocity hurricane zone, which includes Broward and Miami-Dade counties. For those two counties, we have another presentation on how to use the standard RAS 127 for our wind uplift. The Tile Roofing Industry Alliance is a coalition of manufacturers. I'm Wade Shepard and I work for Boral Roofing, one of the members. The TRI is also comprised of associate importers and suppliers. We'll discuss what is the same and different from ASCE 710 to 716, how uplift is calculated, what is the tile ratio. Then we'll use the 6th edition Florida High Wind Tile Manual. We'll work through some examples and present some other updates in the new manual. This presentation is intended for professionals within the roofing industry familiar with or certified to the 5th edition of the FRSA's and TRI's High Wind Tile Installation Manual. These slides explain in detail the changes and updates to the new 6th edition manual. Hopefully you'll find this information useful as you get ready to meet the new requirements of the 2020 Florida Building Code that takes effect January 1st, 2021. As roofing professionals, we have a responsibility to make sure that a roof is designed and installed to meet the code requirements. Here are some examples what can go wrong if they're not installed or designed appropriately. So what is high wind? The International Building Code defines high wind as design wind speeds over 100 miles per hour. The American Society of Civil Engineers determines those wind speeds for every location throughout the United States. Essentially, high wind regions are areas with hurricane force winds, such as Florida, coastal Texas, and Hawaii, or high elevations like the Rocky Mountains of Colorado. Or there's unique geographic features such as Reno, Nevada. The American Society of Civil Engineers develops its nationally recognized standard for minimum design loads for buildings, which is then adopted by the International Building Codes and then is incorporated into the state building codes, and the TRI develops its installation guides to meet those codes. The newest edition of the ASCE 7 standard, ASCE 716, was adopted by the 2018 International Building Code, which was then adopted by the 2020 Florida Building Code, and the TRI developed its 6th edition High Wind Installation Manual for Florida. So what's the same and different from ASCE 710 to 716? The TRI simplified these codes into easy-to-use tables in the new 6th edition manual, as it had done in the 5th edition manual. But we'll go through these changes as it relates directly to the ASCE standards to understand why these changes were made. We'll see that the calculation method is exactly the same, but there are some changes, including that there are more roof zones, higher wind factors, the slope ranges have changed, and the wind maps has changed slightly. We'll review these in more detail. The calculation methods and equations haven't changed, but these are done by certified and qualified engineers when a simpler method, like using the TRI High Wind Manual, wouldn't apply. Pressures are determined for underlayments, and the overturning moments are determined for roof tiles using the equation listed there. What has changed, however, are the gust coefficients. These values have changed for ASCE 716 and in most cases have increased, increasing the overturning moment required, but not for all, and we'll go through some of those examples. The roof zones have changed. From ASCE 710, there were 3 zones for all roofs, 1, 2, and 3, with 3 being in the corners, typically with the highest uplift requirements. In ASCE 716, there are now 6 zones for gable roofs and 4 for hip roofs. They're still numbered 1, 2, 3, But now they have a difference between whether it's at the eave or the ridge or at the other end of the roof, for example, on gable roofs. So they have a 2E or a 2R, depending on whether it's eave or ridge, with different values, or 3E and 3R for ridge or eave corners, and 2N for the ends of the gable roof. The gust coefficient factors have also changed. In ASCE 710, the highest values were in zone 3, or the corner zones, ranged from 1.2 to 2.6. With a new ASCE 716 standard, they now ranged from 2.0 to 3.6, so they have increased in most cases. And these higher GC sub P factors, or gust coefficient factors, directly result in higher pressures for the underlayments and higher overturning moments for tiles, which may require increased fastening. The slope ranges have also changed. They used to break at 5.5 and 12 and 6 and 12, but now they've changed to change over at 4.5 and 12 and 6 and 12. The wind maps have also changed slightly from the previous ASCE 710. So it's good to make sure to select the correct version of ASCE when you're looking up the wind speeds. But it's always best to verify with a local building department to make sure what's the required wind speed for that area or for the project that you're working on. Typically, they will round up to the nearest 10 miles per hour, so it's always best to check to make sure you have the right wind speed. But to look up on your own, there's 2 free hazard tools available online from ASCE and ATC, or AT Council. How is uplift calculated? First, you need to have the following information for the building, the roof, and the tile. You'll need to know the design wind speed, the building width and length, the exposure category, and you'll need to know the roof style, whether it's a gable or hip style roof, the roof slope, the peak and eave heights to calculate the mean roof height, the profile height of the tile, whether it's high, medium, or low, the tile ratio, which is provided by the manufacturers or are in their product approvals, and the installation method of whether it's installed on battens or without battens. You can find the wind speed specific to any project in the United States free online from either ASCE or AT Council at the websites listed here. Using ASCE's hazard tool, simply enter the building location, either using the address, zip code, latitude or longitude, or find on their interactive map. Then select the correct version of ASCE standard, depending on the building code that's in force for your location at that time. Then select the risk category, 1, 2, 3, or 4. 1 is for unoccupied or negligible risk buildings if the building were to fail, such as a barn or storage shelter. Risk category 3 or 4 is for significant risk buildings if they fail. So hospitals, theaters, warehouses of hazardous substances, any place that has a lot of people and if it were to fail could cause significant harm to people. Most tile roofs are typically risk category 2, either they're residential or commercial or industrial buildings. So 2 is typical for most tile roofs. ATC's hazard tool works in a similar fashion. Enter the address or the location and find the wind speed for the risk category that's appropriate. How a building is exposed to direct wind determines its exposure category. Exposure D is where a building is directly exposed to high winds, such as near an ocean or in a large plain or a large lake. Exposure B is where the building and roof is well protected by surrounding objects such as other houses or other buildings or forests, and so they don't have significant direct wind. Exposure C is where it's partially exposed, so that includes all buildings that are not either D or B. Knowing the roof style is also important, whether it's a hip style or gable style. Find the mean roof height by adding the height at the eave from the ground and the height at the peak or the ridge from the ground, adding those two values together and dividing by 2. Tile profile heights are divided into high, medium, or low, as you see here. You also need to know the tile dimensions or the tile ratio. And the dimensions that are needed to be known are the exposed width and the total length. Exposed width is the width of the tile that's exposed when it's installed. So it doesn't include any overlap. That's not the case with the length. You need to know the complete length, the total length of the tile, even what's overlapped. And you take both of those dimensions and they're measured in feet, not inches. So you need to convert dimensions that are typically provided by the manufacturers in inches and divide by 12 to get those measurements in feet if you're going to perform the actual calculations themselves. Instead, however, you can use a much simpler method using the tile ratio in conjunction with using the TRI installation manual. The tile ratio is a simple adjustment factor for the tile size. So the larger the tile ratio, and it adjusts the dimensions, or the values rather, from the tables in the TRI manual to your specific tile. The smaller the tile ratio, and the lower the uplift or overturning moment values will be compared to a larger tile, which will have a larger tile ratio and higher overturning moment values. What is the tile ratio? Tile manufacturers make a variety of different sized tiles, and the tile ratio is an easy way to adjust the wind uplift calculations for different sizes of tiles. The tile ratio values are typically close to the number 1. Larger tiles have higher numbers, and smaller tiles have lower numbers. They are determined from each tile's tile factor. The tile factor is the portion of the equation to determine the overturning moment, and is represented here, shaded in red. B times L with a little a, or L sub a. B is the exposed width of the tile, L is the total length of the tile, and L sub a is the lever arm of the tile, defined as 0.76 times the length of the tile. Multiplying these together, these measurements and measured in feet, gives the tile factor. The TRI tables are based on a tile factor of an older design of tile still used in some parts of the country. Tejas España and Villa concrete tiles made by Boral in Texas are of these original designs, and as you can see, the dimensions here provide a tile factor of 1.407 cubic feet. Smaller tiles have smaller tile factors, and larger tiles have greater tile factors. To get the tile ratio, you simply divide the tile factor for the tile that you're designing for by the TRI standard tile factor of 1.407 cubic feet. Here are some examples of small and large tiles. A smaller tile, Boral's Galena, is only 9 inches wide in its exposed width, multiplied by 17 inches after converting those into feet, to get a tile factor of 1.144. And dividing that by the standard tile factor from TRI of 1.407 gives a tile ratio of 0.813. Similarly, with Crown's Iberia tile, that's much larger and with an exposed width of over 12 inches and the same length, we get a tile factor of 1.541 and a tile ratio of 1.095. So we'll take a look at these examples to see, why does tile ratio matter when calculating uplift pressures and overturning moments. If we look at one roofing square, an area of a roof that's 100 square feet, and compare how many fasteners per square when we use 2 fasteners per tile. If we have a small tile, like Boral's Galena tile, it has 111 tiles per square. If we had 2 fasteners per tile, that means that we have 222 fasteners in that roofing square, or 100 square feet, compared to the larger Crown's Iberia tile that has only 85 tiles per square. When also using 2 fasteners per tile, then we only have 166 fasteners per square. So using 2 fasteners per tile for different tiles is not always the same. It doesn't give the same uplift resistance. So a small tile would have significantly more resistance than a larger tile, unless we use different numbers of fasteners per tile, or different types, such as screws compared to nails. So let's look at the 6th edition Florida High Wind Tile Manual. The first new addition is the Roof Design Product Flowchart, essentially a roadmap of how to do the uplift calculations for both underlayment design and tile design. For the underlayment design, use the exposure category, mean roof height, and basic wind speed to find the required design pressure for the underlayment system on Table 1A. If you're using a 2-ply hot mop system, then you can use Table 1 to find an anchor sheet nailing pattern with a value that meets or exceeds the required design pressure from Table 1A. If using any other underlayment system, use a system that has an allowable design pressure listed in its product approval that meets or exceeds the design pressure determined in Table 1A. Here we see Table 1A. We first look at the roof exposure, B, C, or D, then find the mean roof height to find the right row, and then the wind speed in the column to find the design pressure in pounds per square foot. There's 2 tables for gable roofs and for hip roofs. Let's take a look at the tile design. First, you need to identify the proper Table 2. There are 6 different ones, and each one has a letter, 2 letters actually, after the number 2. The first letter is either a G or H, that stands for gable or hip roof. The second letter is a B, C, or D, which stands for the exposure category. So let's say, for example, you had a hip roof and exposure B, you would then use Table 2HB. Once you've identified the correct table, look up the roof slope, the roof height, and the wind speed to find the values on the table. Those are your overturning moments, and you'll find 2 values, one for LPZ, one for HPZ, and these stand for low pressure zones and high pressure zones. TRI took the many different roof zones listed in the for each roof type and simplified it into 2 categories of a low pressure zone and high pressure zone. Once you found these values, then you can reference Table 3 for the mechanical resistance values for the different fastening methods to find mechanical fastening methods that meets or exceeds these values, or refer to a tile adhesives product approval if you're going to use one of those adhesives. While the 5th edition manual had 2 tables for tiles overturning moments, the new 6th edition has 6 tables. Hip roofs less than 612 have the same or lower pressures. Hip roofs that are 612 and greater have higher values, and all gable roof designs have higher pressures and overturning moments compared to the previous edition. Gable roofs are not as aerodynamic and can act like wings of a plane, creating lift, compared to hip roofs that are more aerodynamic, shaped more like a dome, and reduce uplift. So looking at the tables and comparing the 5th edition to the 6th edition, we can look at, for slopes below 4.5 and 12, they're actually the same values for hip roofs 6 and 12 and less in exposure B. But at 4.5 and 12 to 6 and 12, they've actually gone down compared to the previous table. And the same is true for exposure C and exposure D. Steeper hip roofs over 612 have higher values in exposure B, exposure C as well, and exposure D. Gable roofs all have higher values in the 6th edition compared to the 5th edition. You can see here for exposure B, gable roofs 612 and less, at less than 4.5 and 12, the values are higher, and they're also higher between 4.5 and 12 and 6 and 12. And so is the same for exposure C and D, where they are higher in the 6th edition than they were in the 5th edition. And same is true for gable roofs over 6 and 12. In exposures B, C, and D, they're also higher values. We now have two options for fastening. The single fastening method is similar to the 5th edition, where one fastening method meets or exceeds the requirements for the entire roof, for both the LPZ and HPZ. Now we also have the two fastening methods, where you can use one fastening method for the high pressure zones and a different fastening method for the low pressure zones. To do that, you'll need to calculate the size of the high pressure zones, referred to as dimension A, which is calculated as 10% of the least horizontal dimension or building width, or 0.4 times the mean roof height, whichever is smaller, but not less than either 4% of the least horizontal dimension, the building width, or 3 feet. Once you've determined your design requirements, then you can find a fastening method that meets or exceeds those design requirements. Table 3 provides mechanical fastening resistance values for a range of different fastening methods. And these are the same values that were in the 5th edition manual. Or you can use a roof tile adhesive with a product approval that meets or exceeds the value. So let's work through some examples. Let's take this first example in Naples, Florida. You can see in the picture it's a gable roof. Looking at the Google map, it's surrounded by some homes, but not in a densely built area, so it's not exposure category B, and it's not by an ocean, so it's not exposure category D. So that means it's exposure category C. When we enter the location into ASCE's hazard tool and select risk category 2 for typical residential, we get a wind speed of 166 miles per hour. Let's take a closer look on the map. To determine the building width and length, you draw a rectangle around the entire perimeter of the building. For this calculation exercise, we'll just assume a building length of 80 feet and a building width of 55 feet. Now let's put together all the information that we need for the building, roof, and tile to make the wind uplift calculations. We need the design wind speed. We have the building width and length, exposure category C. The roof style appears to be gable. And let's assume this roof slope is over 612. And let's guess the peak and eave heights of 25 and 33 feet. Adding those together and dividing by 2 gives us a value of 29 feet for the mean roof height. And since it looks like a high profile tile, we'll use Boral's Barcelona 900 tile, which has a tile ratio of 1.084 from its product approval. And let's assume it's installed direct deck with no battens. When using the 5th edition manual to the previous standard of ASCE 710, we would use table 2B for roof pitches greater than 612, because we said it was going to be steeper than 612. And it doesn't matter whether it's a hip or gable roof. We look at exposure C, that section of the table, and we had a mean roof height of 29 feet. We always round up to the next figure, the next nearest number on the table, so that would be 30 feet. And we do the same with the wind speed of 166 miles per hour and round up to 170 on the table. Then we look at the table when we find an overturning moment value of 22.9 foot-pounds force. Now if we use the 6th edition manual to the new standard ASCE 716 and to the new code, we would use table 2GC, G for gable and C for exposure C. The roof pitch again is greater than 612, and again we would use a mean roof height on the table of 30 feet and wind speed on the table of 170 miles per hour. This gives us two values for overturning moment. For the LPZ, or low pressure zone, value of 31.2, and for the high pressure zone, a value of 43.7. Now remember, we need to adjust these values by the tile ratio, which is 1.084 for Boral's Barcelona 900 that I found in their product approval. In the 5th edition, while it wasn't necessary to adjust for tile ratio, we will for this exercise for a comparison. So that value is multiplied by 1.084 to become 24.8, and with the 6th edition, we multiply each of those values by 1.084 and get values of 33.8 and 47.4 foot-pounds force. Now we look at Table 3, the mechanical fastening resistance values, to find a fastening method that will meet or exceed the design requirement. We look at the direct deck and high profile numbers. In the 5th edition, we had a value of 24.8. So looking at those numbers, we can use one number 8 screw per tile, which has a value of 28.7. With the 6th edition, we have a higher value of 33.8. So the value for one screw at 28.7 wouldn't be enough. So we could select another fastening method, and I'll choose to use 2 screws per tile, which has a value of 51.3. The high pressure zone has a design requirement of 47.4. So fortunately, I can still use 2 screws per tile in that zone. So I can use one fastening method across the whole roof. In the 5th edition requirements, I only needed 1 screw per tile, but with the new 6th edition, I'll need to use 2 screws per tile. So now let's look at example 2, which is the same building, but instead of it being a gable roof, let's assume it's a hip roof. Using the 5th edition manual, we would still have the same value. Because it didn't matter whether it was gable or hip design or style, they had the same values. So we still have an overturning moment value adjusted to 24.8 foot-pounds force after adjusting for the tile ratio. Now, if we look at the 6th edition, now we need to use Table 2 HC instead of Table 2 GC because it's a hip roof instead of a gable roof. And we would use or find the area of the table for 6 and 12 to 12, 12 because it's a steep pitched roof. And again, we would look at the mean roof height of 30 feet and wind speed of 170 miles an hour to find overturning moments of 39.5 foot-pounds force for the low pressure zone and 47.9 for the high pressure zone. When we adjust for tile ratio and multiply those values by 1.084, for the 5th edition, we still have the same value of 24.8. And now with the 6th edition, for a hip roof, the values increase to 42.8 and 51.9. Now looking at Table 3, for the mechanical fastening resistance values, for direct deck and for high profile, for the 5th edition, we have the value of 24.8 still, as 1 screw per tile would satisfy all the tiles on the roof, just as we did for the gable roof, because it didn't matter whether it was gable or hip when we used the 5th edition. With the 6th edition, now with the low pressure zone value of 42.8, again, we can still use 2 screws per tile with a value of 51.3, but now with the high pressure zone value of 51.9, that exceeds the 2 screws resistance value of 51.3. Therefore, maybe we would need to use an adhesive that has a product approval value that meets or exceeds the 51.9. If we use the 2 fastener method, we need to calculate the size of the high pressure zones that are highlighted in green and are measured by dimension A. As we discussed before, dimension A is 10% of the least horizontal dimension, or the building width, or 0.4 times the mean roof height, whichever is smaller. So let's calculate 0.1 or 10% times the building width of 55 feet gives us 5.5 feet. 0.4 times the mean roof height of 29 feet equals 11.6 feet. The smaller of those values is 5.5 feet. But it cannot be less than 4% of the least horizontal dimension, which is the building width, or 3 feet. 0.04 or 4% of the building width of 55 feet is equal to 2.2 feet. 5.5 feet that we calculated earlier is not less than this value, and it's not less than 3 feet. So our dimension A is 5.5 feet. So we measure in from the edges of the roof 5.5 feet to determine the high pressure zone, where we would use that different fastening method. And this can be marked on the roof prior to installation of the tiles. Now let's take a look at a third example where it's the same roof, but what if it's mixed, where there's some portions that are hip and some that are gable? How would we deal with that? Well, let's look at an example. So here you see a couple of roof styles that are predominantly hip style roofs, but there's some portions that are gable. The one on the left has a dormer, so it has a gable style roof on that, and the one on the right has an entryway and it's got a gable style roof over the entrance. So if we look at the diagrams of the difference between a gable style and a hip style roof showing the zones, that will give us a guide. Now, first what we do is for the low pressure zones, what we would do is we'd compare the values of the hip and the gable tables and use whichever is higher for that specific roof design, for that type of building and that location with its wind speed and so forth. Then for the high pressure zones, we would use the table for whether it's a hip or gable table, depending on what that style of corner is. We'll use the values we determined from examples 1 and 2 for the hip and the gable designs. We start with the high pressure zones using the hip table for the hip corners, marked in blue, and we found a value of 51.9. which exceeds all of the mechanically fastened uplift resistance values in Table 3. So we determined that we'd need to use foam or a foam adhesive that has a product approval value that meets or exceeds that 51.9 value. The gable corners in green, we found a value of 47.4 and could use 2 screws per tile. For the low pressure zones, we compare the two values between the hip and the gable tables and use the higher value of 42.8 from the hip table and found we could use 2 screws exceeds that value of 42.8. Therefore, we can use 2 screws on the entire roof except for the foam. We'll need to use foam for the hip corners in blue. And to do that, if we use a 2 fastening method, we'll need to calculate the size of that high pressure zone as we determined in the previous example. Let's briefly review other updates in the 6th edition manual issued in 2020. We made some changes to the matrix and provided a whole set of new and improved installation drawings. A couple changes were made to the matrix. Some mechanically fastened systems were eliminated that are highlighted in yellow in the 5th edition matrix on the left. Also, all direct deck systems 412 and greater will require preformed flashings without returns, circled in red in the 6th edition matrix on the right. The installation drawings in the new 6th edition are now full color drawings that are easy to read, easy to identify the different details, as compared to the black and white drawings from the 5th edition. If you have any questions, please contact the TRI at tileroofing.org, or you can contact any one of the tile manufacturers by doing a web search for their name and finding their contact information. Thank you very much.